Serge Haroche is a physicist who has revolutionized the field of quantum physics with his experiments on cavity quantum electrodynamics. He has demonstrated the quantum nature of light and matter by creating and observing states of light that were previously thought to be impossible. His work has opened new avenues for exploring the fundamental aspects of quantum mechanics, as well as for developing applications in quantum information and metrology. He was awarded the Nobel Prize in Physics in 2012, along with David Wineland, for his achievements in this domain. So, hello Serge, it's very nice having you here. You've dedicated your career in the field of light-matter interactions. What kind of phenomena have you explored?
I have tried to explore basic phenomena related to the interaction of atoms with light. So basically what I wanted to achieve in the end was to have a single atom interact with a single particle of light, which is called a photon, because at this level you really see the interaction at the most fundamental level. And in fact, I must say that they have been lucky to enter into this field at the time when the laser was invented. The laser is a fantastic tool to manipulate matter, to observe matter, and this was something which was not clear. When the laser was invented, many people did not know what it would be useful for, and I did not. In fact, I must say that the reality has been much more surprising than the dreams we might have had in the beginning.
So you've mentioned the laser, and during your career you've also seen the development of some groundbreaking technologies that have allowed to push further down what kind of things you can observe. Can you maybe tell about some other physical systems or physical implementations of phenomenology that allowed you to do this?
You have the lasers, you have also the development in cryogenics, which means that you can achieve very low temperatures, which make new phenomena appear, like superconductivity. And you can also use laser light to cool matter at very low temperature. And so this is also something which has developed during the time I was doing my own research. And I have been fascinated by the development in these other fields. I think the privilege when you are a scientist is that in fact, you work in an environment where other people are doing similar things, but with different perspectives, and there is a kind of positive competition, cooperation between scientists, which I think is very important.
It must have been super interesting to see the development of the field as it went and all these different technologies being implemented. But as you've said, it's been a slow development over time. It's taken time, right? And this is what happens in science. Things take time, particularly when you work in basic science. So I wanted to ask you, what is basic science for you?
Basic science is a science that you do because you want to understand things, and you are driven by your curiosity to understand things, to discover new laws. And of course, it's also an unknown territory, so you don't know what you will find, you don't know whether it will work or not. And you are right that it might take a lot of time, because you might go in the wrong direction and you have to correct your trajectory. And of course, it's something that the policymakers have to understand, that the fact that some people want to accelerate things by bypassing basic science and going immediately into applied science, I think this is an illusion and it doesn't work.
So do you think the ability or the possibility of doing basic science has changed over time, over your career?
Yes, I believe that, because when I was young, even until my 40s, when I started to do research on my own, I did not have to justify what I was doing. I was working in an environment in which I just needed to have the trust of the institution. It was possible to get some money from the institution to do experiments which were much less expensive than they are now. And now there is much more bureaucracy. Scientists are asked more to justify their research, to tell where they are going and how long it will take, to have some kind of milestones. Young scientists in particular are more and more obliged to try to put their research within a channel corresponding to a possible application. and that's contrary to what basic science is about. Also, one aspect which is important is that I have been able to work all these years in close collaboration with other PIs, with other people who were as responsible as I was about research, and working with these people, which is a special feature of the lab I belong to, the Castel-Brossel lab in Paris, in which this kind of work with people at the same level is very important. And I must say that I shared the Nobel Prize with Dave Wineland, who was working very far from me. He was working in the United States, but he too was able to work in this kind of collaborative atmosphere.
Since you mentioned David Wineland, you two were awarded the Nobel Prize in 2012. I also wanted to ask you, you belong to a very fine saga of fine scientists. So your PhD supervisor was Claude Cohen-Tanucci, and then his PhD supervisor, Alfred Kastler. All of you are Nobel Prize laureates. Do you think you have a special philosophy of science or way of working that leads to these?
I think that this lab has a special way of working. The fact that young people are being trusted once the leader of the group, which was Kastler, and after Brossel, has decided that this guy is promising, to let him or her develop his own ideas. When I decided to work with Rydberg atoms, I remember I was in Stanford. I wrote a 3-page handwritten letter to Brossel, who was the director of the lab. I explained to him what I wanted to do. I did not say that it would be useful for anything. And he replied immediately, okay, how much money do you need? And I said, oh, I need to buy a laser. Of course, it was the amount of money you need at that time was 1 order of magnitude less than now, but he gave me the money. And he never asked me to write reports. The reports were just the papers that we published. And so this atmosphere has gone on for a long time in this lab. Now it's a little bit more difficult because the amount of money that we need cannot be obtained in the lab, so we have to apply for grants. But once you have been recognized, it's easier than when you start. So I think this atmosphere of freedom and of trust was very important. There are some families of Nobel Prize winners. When you get into this system, you have more chance. Dave Wineland was also the student of Norman Ramsay, who got a Nobel Prize, and Ramsay was a student of Isidore Rabi, who was also a Nobel Prize winner. So you had this kind of family prizes, which is something which is helpful. And I know it's true in other fields. In chemistry too, you have had the same.
After a lifetime of very significant contributions, what question comes to mind that you would like to see answered?
In the domain of manipulation of systems, one by one, the kind of physics I have been doing, many things will happen, not only in cavity QED, but in other areas. And people hope to be able to simulate what happens in condensed matter physics by just arranging atoms in well-defined, well-controlled structures. You can achieve also much higher precision in measurements. And I have been amazed by the progress of atomic clocks. The first clock in science was a clock that Huygens developed in the 17th century. It was beating at the period of about 1 second. And the atomic clocks, which were used for the GPS, had a frequency of 10 to the 10 per second. That is 10 orders of magnitude more faster than the pendulum clock, and the precision increased by the same amount. And then in the last 20 years, the frequency of the clock has increased by another 5 orders of magnitude because we went to optical frequencies, and the precision has increased by the same amount. And the precision of today's clock is unbelievable. If you had started the 2 clocks at the beginning of the universe, they would not depart from each other by more than a tenth of a second. This allows to measure gravitational effect, general relativity, and this brings me to cosmology. In fact, these clocks might be one day useful to detect gravitational waves, and this raises an issue of what is the connection between quantum physics and gravitation. And this is a big question today, and whether this will be useful for something is not clear, but maybe, and certainly, and I wish I could see future development in this domain.
Yeah, but from other responses of yours, whether it's useful or not, is not really...
No, it always ends up by being useful. For example, the fact that the internet was developed at CERN to just propagate data faster and to you never know what will be the application of even very abstract and very fundamental research not related at the start with any application. And in fact, different domains rely on the same kind of ideas. For example, for attosecond lasers, you need to use at the start frequency combs, which allow you to make very fast and repeatable pulses. The frequency combs are essential for the optical atomic clocks. And so these two fields, which have nothing to do with what they are doing, rely on the same kind of technology. And these laser combs, which have been made possible by a process which is the mode locking of lasers. And mode locking is an idea that Huygens developed in the 17th century to lock two pendulums together. So you see that all these ideas, even the ideas which will lead to applications, come from basic science over the centuries. And I think this is another privilege that we have as scientists. We not only belong to a community, geographical community at a given time, but we belong to a community which has its roots in the past. It's not because quantum laws have come that we have to disregard what people did before, because it's still, even to apply quantum technologies, we have to rely on ideas which we originated much before.
Here at our institute, we have a lot of students. What would be your advice for them if they wanted to get into physics or science?
First of all, have a good background in mathematics, to have a lot of passion for that, for knowledge, and for acquiring the idea that it's important to acquire new knowledge. And you have to have a passion for one specific field. That's important. And you have also not to feel overwhelmed by all the knowledge which has been accumulated before you, because that might be a little bit too impressive on young students. So you have to know that there are still things to be discovered.
Thank you very much for your time.
Thank you.
And it's been a pleasure having you.
And your questions were very not provocative, but very made me think a lot about important issues. So thank you.
Thank you very much, Serge.